Good day, everyone. My name is Rivera Diaz, and today I'll be presenting my course project on using machine learning to detect network intrusions. The central idea is pretty much, it's straightforward. Um, can a trained algorithm reliably tell the difference between normal network traffic and malicious attacks? Faster, more consistent, and more useful than traditional rule-based systems. Let's walk through how I approach that question. In order to understand why this project matters, consider the scale of the problem. IBM's 2023 costs of a data breach report found that the average breach costs organizations 4.45 million. Traditional intrusion detection systems rely on predefined rules. They work well for known attacks, but the moment an attacker changes their approach or uses a new exploit, those rules become useless. That's the gap this project aims to address. The dataset I used is the NSL KDD dataset, which it's very accessible. It's a publicly available benchmark created by the University of Brunswick. It contains nearly 126K training records and over 22K test records, each with 41 network traffic features and a label identifying whether the connection is normal, if it's within range, or a specific type of attack. There are 5 classes in total. Importantly, the dataset had 0 missing values, which made pre-processing easy, straightforward, clear, concise, just to the point. Rendering and processing. Once everything was loaded, I ran through a clean 5-step pre-processing pipeline. The data was already complete. There were no missing values anywhere. I created a binary target column, encoded the 3 categorical text columns using label encoding, and removed 2 columns that were not relevant to real-world detection. The final dataset was 125,973 rows by 42 columns, fully numeric and almost perfectly balanced between normal and attack classes. Let me highlight 2 of the most informative visualizations. On the left here, you can all see that the TCP traffic dominates overall, and attack traffic makes up a much higher proportion of ICMP connections, which confirms ICMP-based flood attacks. On the right is what I found most interesting. The SYN error rate shows a bimodal distribution for attacks. Normal traffic clusters near 0, but attack traffic spikes at both ends. The high ends spike is a signature of a SYN flood DOS attack, where connection requests flood in, but the handshake never completes. Before building the model, I ran a correlation analysis to identify which features have the strongest relationship with the attack label. The top 4 are all variations of the SYN error rate, each correlating at around 0.69. The negative correlations for logged underscore in and same underscore SRV underscore rate make intuitive sense. Normal connections are more likely to result in a successful login and tend to stay on the same service. This analysis directly informed my feature understanding going into modeling. I trained a random forest classifier with 100 trees and a max depth of 20. The results speak for themselves. 99.73% accuracy and a ROC AUC rock hook of 0.9991 on the held out test set. For comparison, juxtaposition, a logistic regression baseline achieved around 92.71% accuracy. That gap is significant in a real security context. Every percentage point of missed attacks represents real intrusions slipping through undetected. Looking at feature importance, the four SYN error rate variants together account for 66.5% of the model's decision weight, which directly validates what the correlation analysis showed us earlier. The confusion matrix tells the full story. Out of 25,195 test records, only 68 were misclassified. So take that number a little bit over 25K and only 68. That means 33 false positives, normal traffic flagged as an attack, and 35 false negatives, actual attacks that slip through for a real world IDS. That's an astounding result. Alright, everyone. Process all this information and we are wrapping up. The results confirmed our hypothesis. A random forest classifier can accurately distinguish benign from malicious traffic with over 99% accuracy, significantly outperforming a logistic regression baseline. The motto is interpretable, fast, and practical. The main limitations are the age of the dataset and our binary classification approach. Future work should test on more modern datasets and explore multi-class models. I'm happy to take any questions. Feel free to email me or ping me, maybe on the comments in class, and connect with me on LinkedIn. I would love to connect with all of you. Had a lot of fun, learned so much using all of this in real life and work. I am Don Rivera Diaz. Have a great one, everyone. Thank you.